Okay, let's say we have a container of steam, or H2O. So given H2O, and this is going to be a vapor. In other words, a superheated vapor, all right? I have a pressure and a temperature here. We have a pressure is equal to 120 bar, and we have a temperature equal to 520 degrees C, 520 degrees C. Okay? Let me show you a schematic here. So we have a container. So here's our H2O. And this container has a certain temperature, a certain pressure, a certain volume, and a certain mass, okay? So I want to find some things. Find. First of all, I want to find the specific volume. Find the specific volume. So this will be the first part, part A. Let's find the actual specific volumes using superheated vapor tables. So specific volume using superheated vapor tables. This is going to be my actual specific volume. The tables are correct. The tables give you the specific volume. And then I'm going to use the compressibility factor and find specific volume using compressibility factor Z. And then I am going to attempt to calculate specific volume using the ideal gas law. So V, ideal gas law. Okay, I will attempt to calculate specific volume using the ideal gas law. All right, we'll see what our success is there. We'll see what our success. Okay, let's get started. So analysis. Part A. So specific volume is equal to specific volume of a superheated vapor. I'm telling you it's a vapor. You'll see in a minute that it is. Evaluated at a temperature equal to 520 degrees C and a pressure of 120 bar. 120 bar. Okay? Let's go to superheated vapor tables. Let's go to superheated vapor tables in the notes. So B1, saturation temperature table, saturation pressure table, superheated vapor table. Pressures are located in the header. Let's see if we can find a 120 bar here. This is all table B4. They're just a bunch of tables being continued. 120 bar. Here's 120 bar. Temperature is given here, pressure is here. Let's see, 520 degrees C. 520 degrees C, 120 bar. The specific volume with units of cubic meter per kilogram is 0.02781 equals 0.02781 cubic meters per kilogram. 0.02781 cubic meters per kilogram. Okay? 0.2871. And this is from superheated vapor table. Superheated vapor table B4. Okay? So specific volume for part A is 0.2781 cubic meters per kilogram. Let's put a box around that. That is the actual or the true specific volume. The table, the superheated vapor tables are accurate. Let's move on to the compressibility factor. Let's see if we can estimate specific volume using a compressibility factor, Z. Oops. Okay, so we have our, so let's start working on B over here. Start working on B over here. We got our equations, definitions for compressibility factor. Now I want a specific volume out of one of these expressions. Specific volume is not volume divided by the number of moles, it's volume divided by mass. So I'm going to write that first equation. I'm going to write Z is equal to PV over M RT, and then I'm going to group the volume and the mass together, and I get volume over mass, and then I have P RT. Now this, of course, is specific volume, and so I get specific volume PRT. Let's solve this for specific volume. Specific volume is equal to the compressibility factor times the gas constant T times temperature divided by the pressure. All right? Now I have temperature, I have pressure, I don't have the gas constant R, I'm going to have to calculate it, and I don't have the compressibility factor Z. I have to look that up or calculate it as well. Okay? First of all, let's get the gas constant. Let's get the gas constant. Let's get the gas constant. So, how do I want to do this? Got this in your notes? Hope so. I'll start working on the gas constant. Let's see here, R. R is equal to the universal gas constant divided by the molecular weight for the material. Okay? Now we have H2O, so molecular weight for H2O, what is that? Let's go to our text, our notes, and let's look up the molecular weight of H2O, water. Let's go to table B1. Water, molecular weight, 18.02 kilograms per kilomole. 18.02 kilograms per kilomole. 18.02 kilograms per kilomole. And that's from B1, okay? So that means our gas constant, R, is equal to 8.314 kilojoules per kilomole, degree in Kelvin, and then I'm going to divide that by the molecular weight. This is RU right here. Divided by the molecular weight, 18.02 kilogram per kilomole. The kilomoles cancel out, and I get kilojoule per kilomole, degree in Kelvin. And I get a gas constant, and this is going to be for H2O. So R, H2O. So we're going to have clear 8.314 divided by 18.02. 0.046. 0.461, and that's going to have units of kilojoule per kilogram degree in Kelvin. Kilojoule per kilogram degree in Kelvin. Okay? Kilojoule per kilogram degree in Kelvin. So that's R for H2O. So now I got R for H2O, okay? Let's get the compressibility factor. That's the last thing I need. So what is Z? Z equals what? What is Z? Well, first of all, let's go back and look at our compressibility chart. What do we need to know to calculate the compressibility factor Z? So Z is a function of reduced pressure and reduced temperature. Remember, reduced temperature and pressure are temperature and pressure divided by the critical temperatures and pressures. So let's calculate the let's calculate the reduced temperatures and pressures. So Z is equal to, so let's calculate the reduced temperature and pressure. So T reduced is equal to T divided by T critical for H2O. Let's see, the temperature is 520 degrees C. Critical temperature and pressure are going to be in Kelvin, so I need to add 273 to get it in Kelvin, degrees Kelvin. So let's look up the critical temperature for H2O. Let's look up the critical temperature for H2O. Table B1, critical temperature, water, 647.3 degrees Kelvin. 647 Kelvin. 647 degrees Kelvin. Kelvins cancel out, and I get a reduced temperature. Let's see here, 520 plus 273, divide by 647. I get 1.225. Okay, that's the reduced temperature, 1.225. What about reduced pressure? What about reduced pressure? P reduced. Well, that's equal to the pressure divided by the critical pressure. Let's see here, we got 120 bar. That's the pressure. What's the critical pressure? Let's have a look in table B1. Critical pressure for H2O, 220.9 bar. 220.9 bar. So I'm just going to put 220 down there. 220, 20 bar. Bars cancel out. Reduced pressure is dimensionless. And I get 120 divided by 220. 20 divided by 220. 0.54. Actually, 0.55. By the way, if you're thinking ahead on using the ideal gas law, where Z is approximately equal to 1, we're already in trouble here. Remember the criterion for using the ideal gas law is reduced pressure must be less than 0.2. We're at 0.55, almost 0.6. So clearly for part C, when we calculate specific volume based on the ideal gas law, we're probably not going to get a good result. Okay? In any event, reduced temperature and pressure, 1.2 and 0.5. So Z evaluated at a T reduced equals about 1.2 and a P reduced about 0.5. Let's get the compressibility factor from our compressibility chart. This is going to be kind of an eyeball affair here. It's going to be kind of an eyeball affair. Let's see here. There's our compressibility chart. So 0.5 is our reduced pressure, so we're along a vertical line going through here. And reduced temperature, what was that again? That was 1.2. Here's 1.2 right here. Here's my 1.2 reduced temperature line, that solid line. So I'm at 0.5 reduced pressure, and I go up to the point 1.2, 1.2 reduced temperature line. Looks to me like I get about 0.9 for Z. Somewhere right about here. You could use a pencil and a ruler and probably get a better result. But it looks to me like Z is going to be about 0.9, okay? Maybe a little higher, maybe 0.91. I guess it's probably 0.91. I'm going to put that in. I'm going to choose 0.91. So Z is approximately 0.91. 0.91, okay? And that's from the compressibility chart. Compressibility chart, all right? Okay, let's finish the calculation here. Let's calculate the specific volume for our H2O. We now have the compressibility factor is 0.91. So 0.91, gas constant 0.461, and that has units of kilojoule per kilogram degree in Kelvin. The temperature, Kelvin. Kelvin is the temperature unit in the gas constant, so we have to give temperature in Kelvin, so that's 520 plus 273. So what? That's going to be 793 degrees. 793 degrees Kelvin. And then the pressure is 120 bar. Okay? So let's crank some of this out here, and then we'll deal with the units in a second. Looks like we have some unit issues. So 0.91 times 0.461 times 793 divided by 120. And I get 2.77 something. Let's look at the units here. Well, the kelvins cancel out, that's good, and I get a kilojoule per kilogram bar. Whatever that is, that doesn't look like a density to me, a specific volume. Specific volume should be cubic meters per kilogram. Well, let's try to, first let's get out of the bar and let's get into kilopascals. Let's get out of the bar and get into kilopascals. Let's see, there are 100 kilopascals per bar. So 1 bar equals 100 kilopascals. So the bars will cancel out. So I divide that by 100 and I get 0.0277. And now I have a unit of kilojoules per kilogram kilopascal. Okay? Kilojoule per kilopascal, kilojoule per kilogram kilopascal. Okay? Let me get over here and work on the rest of it. Get over here and work on the rest of it. Let's see here. All the way over here. Okay. Well, let's get out of the kilopascal and get into pascals. So 0.0277. And then I've got kilojoule per kilogram. And then I got a kilopascal. Let me get out of kilopascals and go into pascals. Let's see here. There is 1 kilopascal per 1,000 pascals. Kilopascals cancel out and I get pascals, so I got to divide it by 1,000 again. By the way, I think I'm going to convert out of the kilojoules too. Let's do that. Let's see here. There's 1 kilojoule per 1,000 joules. And actually, if I do that, the 1,000s cancel out in the conversion here. And so I end up with 0.0277. And the unit I have left over is a joule. So the kilojoules are gone. and I have a joule per kilogram, and then I have a Pascal. Now, a joule is a Newton over a meter. Newton times a meter. A Pascal is a Newton per meter squared. All right? The Newtons cancel out. The meter squared goes at the top, and I have cubic meters per kilogram. 0.0277 cubic meters per kilogram. In other words, specific volume using the compressibility factor. So I'll say compressibility factor is equal to 0.0277 cubic meters per kilogram. Okay? Now let's compare what we got using the tables. Using superheated vapor tables, we got 0.0278 cubic meters per kilogram. That is the specific volume at that temperature and pressure. Using the compressibility factor Z, which we found to be equal to 0.91 using the chart, we get something very similar, 0.0277. Very close. And I was just eyeballing the chart. Okay? So the compressibility factor approach actually did pretty good. Good agreement with superheated vapor tables. Superheated vapor tables. Good agreement. So if you want to calculate some quantities for a gas, you can either use superheated vapor tables or you can use the compressibility factor and the compressibility chart. Okay? Now I'm going to take a pause for a second. We're going to finish up part Z, which is assuming the ideal gas law and cranking away. But I'm going to take a break for a second.